better image of Lambertian lighting. So in this picture, basically the light source is somewhere over here, and this is probably where 1 is. I mean, where 0 is. And then we kind of go towards, 50-50 gray, maybe somewhere around here. Then we very quickly seem to get over to 1. And as you can see, what's going on behind here is just that it's pure black, and the edge is kind of pure black. So this kind of makes sense that everything inside of the shadow of the half sphere is not receiving any light, so it should be black. However, in real life, this light that is hitting this sphere, it's not just hitting the sphere, it has to be hitting other things that are around the sphere. So it could be hitting a wall, it could be hitting trees, it could be hitting a dog, it could be hitting particles in the air, and so on. And so everything that the light hits can reflect it and also refract it to some degree. But we're only basically concerned about the reflections that come off of all these objects. So let's also pretend that these spheres are actually around here, and not just this one. So light hits this and it hits this, but the light that hits this bounces and hits that, and then hits this, and light that hits this bounces and hits here, and hits over here, and hits over there, and hits back here, and eventually bounces it all around, and there's all these different photon bounces until eventually it gets to the point where there's some light that's able to illuminate the backside, so it's not pure black anymore. But if you have a video game, the one way that you could avoid having this happen is have a second light back here. Put a light back here that is a really low intensity, and then this section will no longer be pitch black, which is kind of cool because it kind of represents what's going on in real life. However, instead of just having one single light, what you would really have is probably pretty much an infinite amount of lights back here that have really low intensity, that are basically on the surface of all the objects that are around the object that you're focusing on. However, that's impossible inside of a gaming engine, so you basically just fake it with another light back here, or sometimes multiple lights back here. I believe at one point they used to kind of create a light dome so that you could fake global illumination, because in all honesty, global illumination is basically what's creating a light source for the backside, and it's the reason why it's not pitch black in real life. So basically, global illumination is the reason why you don't have any like super dark areas, or the light source is actually coming kind of from over here. So the reason why this area isn't pitch black is because of global illumination. The reason why the shadow isn't pitch black over here is also because of global illumination. And the reason why the shadow is tinted is also because of global illumination. So Lambert diffuse does not take into account of global illumination, and it also kind of has a harsh fall off, because in all honesty, I cannot necessarily say that 45 degrees away from the light source is necessarily 50-50 gray. I said that it was because it kind of makes sense, but I don't believe that the fall off is actually allowing 50-50 gray to appear at the 45 degree angle mark. Or even if it does, it doesn't look like it. It doesn't look like that's what's happening. And it may be, you might be able to actually test that it is at 50-50 gray at the 45 degree angle if this diffuse color, the base color, was white. Because if the base color was white, you'd be able to tell where it was 50% black and 50% white. But if you have a base color that's gray, it's kind of hard to tell where your 50% mark is. But that's basically how Lambertian diffuse appears. Now, I want to say that the Lambertian equation is actually a whole lot more complicated, and we don't use the full equation. So this is sort of a Lambertian approximation, is what we actually use in gaming. So, like, now let's say you want to fake that global illumination, and you also don't like that harsh fall off. So now you can go with a half Lambert or a wrap light. So, or wrap lighting. So, from my understanding, half Lambert appeared in Half-Life 2. And so basically what you're doing is you're taking Lambert and you're kind of dividing it mathematically. But then wrap lighting is a bit different. So, we're actually going to use wrap lighting instead of half Lambert in this shader. But, in all honesty, half Lambert and wrap lighting isn't like, let's say, it's eyeballing. It's not necessarily physically accurate based on you can't just put in an equation of lighting and expect it to be able to exactly model what this particular material is going to do. You basically have to eyeball and adjust the range yourself. But there is something that is a little bit more technical. And so half Lambert and wrap lighting is making Lambert softer and faking global illumination, but that may not have been its original intended purpose. It may have been basically trying to create an approximation of another lighting model, which is not Lambert. There's another lighting model which exists. I wonder what. Okay, there's another lighting model that was created to model the full moon, and it's I'm probably going to butcher this. It's oren-nayar diffuse, and it was made to model extremely rough surfaces. It was also not the only model for the full moon. So there's another one. I don't exactly remember its name. I think it starts with a B or something. But here's another example of oren-nayar, and it was taken to better model an extremely rough surface. And when I say extremely rough, I mean rough like that other shoe that I was showing you that was leathery. But the suede shoe, except for we would be looking at that suede shoe probably pretty far away instead of up close, so you wouldn't really be able to see individual highlights coming off of individual naps of the suede. So again, we would be looking at it pretty far away, and generally all these lighting models that are supposed to be modeling a rough surface are assuming that all of the roughnesses of the surface are uniform, and that you don't have any parts of the surface that's more rough than other parts of the surface. But in this real image, you can see that it doesn't quite have uniform roughness. It looks like this is a little bit more rough than this area over here. But in the Lambertian model, it's pretty much evenly rough, and also in the oren-nayar model, it's also evenly rough. But what you probably notice is that the fall off is a whole lot more gradual and closer to the real image than the Lambertian model. So basically what we can say about the Lambertian model is that it is made to model a rough surface that is not in a situation where there's a lot of global illumination. So it would probably be a pretty good model if you had a character that was being lit up by a candle and they were outside at nighttime, and it was like medieval, during the medieval times where there wouldn't be a whole lot of external lighting. So basically you would just have the candlelight illuminating one side of the model, and then the other side of the model would be pretty dark because there's not much global illumination um, during a scene like that. But the oren-nayar model would be better for indoor lighting. Like, let's say you have, oh, you're inside of a room, fairly large room that has quite a bit of furniture in there. Also has quite a few windows. You have light, external light from outside coming in, but the light isn't like say having the sun shine directly in the window. Or maybe you could have that, but the model is still fairly rough, so you don't have a specular highlight from that. And so what's basically going on is all that sunlight and external lighting from the outdoors, because you'll have light coming from the outdoors even if the sun isn't out, if it's behind a cloud or whatever. But all that external lighting is bouncing around, creating global illumination inside of the building. And so you won't get these drastic fall offs, and you'll get something that looks more like this. And so you will model that with oren-nayar. But oren-nayar is computationally expensive because there's some trigonometry that has to be done in the code, and so the machine has to process some trigonometry, which makes it a little bit slower. So I think that wrapped lighting may have been created to fake the oren-nayar model. So the wrapped lighting kind of behaves like your oren-nayar model because it has less of a fall off, except for the oren-nayar model has a very specific fall off that's related to the function. Well, not related to the function, but it's related to a roughness variable. So you set the roughness, and then it does the calculations on its own to tell you how much fall off there should be. So it basically goes from a Lambertian lighting model for 0% roughness, and then it goes to probably actually no fall off, where this would be pretty much a flat image, kind of like how it is over here, where you don't really see much of any shadowing at all. So basically there's internal calculations that it does on its own. With your half Lambert is a very cheap series of calculations that has doesn't quite look exactly like wrap lighting, but it basically is half Lambert, and it's set. And as far as I know, there's no roughness variable, so it would basically probably come out looking like something like this all the time, no matter the roughness of the object. And there's no I think the fall off is a little different than the oren-nayar model. The wrap lighting, you can attach a roughness variable to it, so that it would you'd be able to change it like you can with your oren-nayar model. But there also can have calculations for not just the fall off, not just having the fall off linked to the backshade of the model. So if you were looking at the model, if you were standing back here, so if you're standing back here where -1, if you were standing in a place where -1 and 1 would be located at, that can have a different darkness to it than the fall off. So in half Lambert, the fall off and the color that, or the shadow behind the model, is linked together, and that's the same way it is for the oren-nayar model. So when you change the fall off, you also change the color behind it, where the -1 would be, and the N.L projection, or yeah, I guess that's the best way to put it, the N.L projection. But you can have a wrap diffuse where you can change the fall off, but then the color on the non-lit side of the model can be extremely dark or extremely light. In other words, you can change them independently. But the independent changing is, that's not handled internally by the function. You would have separate sliders, separate properties that you could change by hand. So that's not something that's just being, you know, output by the lighting function just automatically. It is that way when you're linked. Lambert is linked, but you can't really change what's behind there from being perfectly black anyway. With oren-nayar model, I don't remember if the backside of this is actually pitch black. I'm thinking that it's probably not. And with half Lambert, it's definitely not pitch black back here. With the wrap lighting, you can make it pitch black. You have the option of basically being able to uncouple the backside color and the fall off. I've said that pretty much a million times already, but from these pictures you can't really see what's going on. When we get into the coding section, maybe I'll show you a half Lambert versus a Lambert versus a wrapped, and then maybe if I have a good oren-nayar that's working, we can look at that as well. But that's basically the diffuse lighting models and how they work, and why we probably are better off not using the Lambertian lighting model in most situations. It is only applicable to a situation where you don't have much global illumination, and then you need to use a half Lambert or a wrap diffuse, which you have more control over, or an oren-nayar, in pretty much every other situation. So that's my explanation for diffuse lighting models.